Thank you. Thank you. Hello, everyone. So, yeah, I'll just start with the basics, like what we did the last time. So we have our course website for people that should familiarize with it. So you can like click on courses, and then this is the course. So what we did like last time, we just spoke about just some intro basically, and then we spoke about measuring efficiency. So I included some slides which were basically describing all this part of about memorization. So right now just was like go through like some through our discussion we'll basically be talking about comparing orders of growth. And then we released our assignment here. So we just said like, not a lot, just 5 problem sets. So answering all 5 was not a requirement. At least like, if you manage to answer 2 of them, then you're good. So and then we also included, these other, the last 2, for extra challenges. And then you are meant to like get the code from here. I understand that like, so the first question for the code, there was like an error in some doctors, but I sent like I think a message on WhatsApp telling people how to correct that error. Apologies. And then here we put in the lecture video for the the screen recording for our previous lecture. And so today we're just going to have a discussion. We're meant to start like at 9, but then we're late, but then we're still going to maintain this time, like, to end at 11, so that people, they can attend to what they had planned to do today. So right now we won't just be like going through much. So I can share my screen, and then we can start like solving one problem after another. How does that sound? So this is not like more of a lecture, it's a discussion. We can talk together. Actually, I'll be asking people questions along the way as we get to solve this. So we'll be solving it together one step at a time. So okay, let me stop sharing and then connect something. So okay, yes. People can see that. People can see that. Thank you for responding. So if you want to ask anything, you can unmute your mic. Make sure that like you don't have much background noise, and then we can talk. And then I'll be asking questions, like also checking the chat just to see if we're still together. Okay. So I want to start about just just giving like some kind of prologue. Like if you look around you, like there are computers and like networks everywhere. So like how maybe our last years have kind of been like in education and commerce and entertainment, research, manufacturing, health, and so many things. Even like when it comes to defense, like countries they spend so much time, like, you know, they rely on computers to really scale up most of the problems which they might have. So one thing which is a driving force towards the use of this is knowing how to write algorithms which are more efficient. So just like, you know, just to talk of about algorithms, let me increase the size of this. Yeah, just to talk about algorithms. Okay. So our goal mostly is to create algorithms which are what? Yeah, efficient. So, you know, when we write our code. So like, yeah, if you think of, you know, the time back in the, you know, in the dark ages, like when, you know, before, like I knew in primary school, we used to learn that, you know, before people could just count using what? Using Roman numerals. Like, for example, if you wanted to represent the year uh, 1448, for example, in Roman numerals, you have to know that it can be like, you know, like, can what? You know, that millennium, that 1000, and then you have to have 500, but you have to subtract. Okay, so this is what? 1400, and then you have to like add 40, but 40 is what? It's XL. Then you have to add in, like, you know, the 8, 111. So like this was how, like, you know, how the Romans used to, like, for example, represent numbers. But then, for example, like, you know, just thinking of how how do you add how do you add such numbers? Let's say you have this number, and then you just have another one, maybe like let's say you have one. No, I'm just like, yeah, coming up with just some random number here. So you have such, yeah, yeah. How, if you were to add this, how would you add this? So this just looks, you know, like more complicated. But thanks to, like, you know, around 500 years, like 80, you know, we just got like this cool concept of, like, you know, the decimal system. So now we can like kind of rely on it. It has really like given a revolution in terms of how our quantitative reasoning. So now I want to talk about, like, you know, this guy who had like Leonardo Fibonacci, you know, who started the Fibonacci sequence. So on our previous lecture videos, we spoke more of that, but I want to use that as a way of introducing the big O. So let's look at Fibonacci. Okay, so we know that Fibonacci's numbers, they are these numbers where you have 0 and 1. These are the base numbers, but then you add the two previous numbers to continue getting the numbers which you want. Okay, 13, 21, 34, and then you can, like, you know, you can continue. So like, how can you like think of this definition? For example, let's say if f of n, if this was your Fibonacci number, so how are we generating them? So basically we have like some kind of a piecewise function. So what we have is, we have 0 and we have 1. Okay, and then we're saying if your n is 0, and then you just what, you know, like, if n is equal to 0, you get 0. If n is equal to 1, you get 1. But then if n is greater than 1, what are you just returning? You're just returning the result of calling f of n minus 1 plus f of n minus what? N minus 2. So this, like, you know, this way, or this sequence, this simple rule, just allows us to, like, you know, to compute the Fibonacci sequence, you know, by just like having a given number. So now if you look at it like, from a mathematical standpoint, this looks like no so reasonable. Like, like what's the fib of 1 million? You can like, that there's a rule to, to look at this. So this the Fibonacci sequence has been studied so much, and also like the other favorite numbers in computer science, the Fibonacci sequence. I think also the powers of 2. Those are very good sequences. So now let's look at like if when we defined our code in Python, let me use a different color for the code. Okay, so when we defined the Fibonacci sequence, what did we say? We said like, if n is equal to 0, okay, we just what? We just return 0, like else, elif, okay, elif n is equal to 1, we just return 1, else, what do? We just return Fibonacci of n minus 1 plus fib of n minus 2. So basically now we've just taken this this mathematical rule, and what we have done is we've taken this rule, and what we have done is we've just translated it into code so that a machine can recognize it. So if we look at if we look at this algorithm, what can we think? We can say, okay, here we've like implemented written the algorithm. So whenever we have an algorithm, these are the questions which we have to ask ourselves. So when you have an algorithm, so that's what the interviewers will also be asking you. So when you have an algorithm, the first question which you should ask yourself is it correct? Okay. So is it correct? Like they give you a question, just try to find, okay, can you like get it to work? So when you have found out that it's correct, then you can also ask another question, like how much, maybe like, time does it take as a function of n? Now that would be like, looking at the mathematics today. And then after you've like analyzed how much time it can take to run the operations of that function, then you can ask yourself like, okay, can we do better? Okay. So if you have asked yourself these 3 questions, then now you can say, okay, yeah, we can do better. And then like, you can then like say, okay. So now let's try to use these 3 questions to look at the Fibonacci algorithm. Okay, the first question, is it correct? Yeah, if we look at this, yeah, it looks correct. Because we just basically translated a mathematical rule which was there. And then, but now if we say, how much time does it take? Okay, so like this now, when you say how much time does it take, now it demands an answer because we have to really know. Okay, so by time, let's try to measure it using like some computer steps, like the number of operations which need to be taken. So let's have maybe like some expression. Let's just say let t of n be like the number of computer steps. Okay, so like needed to compute like fib of what of n. So now, which means T of 2, for example, now, like e.g. T of 2, will be the number of steps which give us what? Fib 2. So like, just measuring, that. So now, how can we look at it, for example, like, how can this T of n be useful to us? So what happens, for example, if n is less than 2? Okay. So if n is less than 2, we're only just looking at these cases, like when n is 0 or 1. So how many steps, like it's, if n is less than 2, then you can just say that, okay, yeah, like the number of steps, like if n, this is not code, this is just English. If n is less than 2, then like, you can just say that our T of n, like, should, it's also like less than or equal to 2, for n less than 2. Okay. So like, I was saying, okay, the number of steps is just like, no, it's trivial, like, because our program just stops immediately, when it just checks, like, if it gets n and then it just does this check and comparison and then it just returns. So, we just like, we get nothing interesting from there. But then now, what happens for larger values of n? Since we have two recursive invocations of the Fibonacci, of the Fib function. So we say that in this definition, say let T of n be the number of computer steps needed to compute Fib n. So which means now, using that definition, then the number of steps needed to compute, let's say, for example, to compute T of n minus 1. These are the number of steps to compute T of n minus 1. Then if we add the number of steps maybe to compute T of n minus 2, okay? So we'd want to, like, maybe get something like, like T of n. Of course, to be precise, we know that we have to, maybe add, like 3 here, for example. Like what we do is we have the number of steps to calculate this Fib n minus 1 and this Fib n minus 2. So that we have T of n minus 1 and T of n minus 2 there. And then we'll then add, like the last, we have one more step, for example, like when you have the number of steps from here, we just like a check on the value of n, and then like, plus like final like addition, because you can like check there and check there. That's one step. Yeah. Okay, this is one step, checking the value of n and also checking this value of n, and then plus what? Adding these ones. So that's where, like, that 3 comes from. So what we now have here is, like what we can like think of it as, like they give it the name, it's like some kind of, okay, recurrence relation for those who might want to look at this more further. But then we're not going to like now go much deeper like in the mathematics. We're just going to see how this thing actually, like, why we need to write a Fibonacci function which has to perform better. So if we look at this relation, let's try to compare it with with the Fibonacci sequence. We know that we had I said Fn is equal to what? To f of n minus 1 plus f of n minus 2. So if we are comparing these two, we can immediately see that, T of n would be what? Will be greater than what? Than f of n, because this, looking at this runtime, already we know that, okay, now this is bad news, because this algorithm, it grows as fast as the Fibonacci numbers. And we know, like, the Fibonacci numbers, they just keep on, like, increasing. So what we can just say is, like, this T of N is exponential in N. Okay, so if people questions, ask on the chat, I'm like looking at the chat right now, and yeah, okay. So T of N is exponential in N. And then now, how can we, like, maybe, like, let's try to see what happens when we want to compute F of 200. So in order to compute Fib 200, then the algorithm has to take, the number of steps can be, that's T of 200, but already we know that this is what is greater than F of 200. So now there's this rule which like tries to call, which approximates, when people are starting the powers of 2 and they're also starting the Fibonacci sequence, there's a general rule which says that F of N is approximately equal to 2 times 0.0694 of N. So basically, like, if we have F of 200, what we're going to get is, basically we have like 2, okay, I think, yeah, okay. So yeah, you're basically just going to get, like, 2 times some other, like, higher value, for example, 1.38. So this is like when we say this up, like this number of steps, okay, when you say that they are greater than F of 200. And now let's try to see what F of 200 is approximately equal to in terms of the number of steps. Let's say, like, you have to take these computer steps, which can be either like adding, addition, or comparing. So now, how long, for example, it will take to compute this? Like, of course, it's dependent on the computer speed. Like, computers, they're getting faster today. For example, like the NSA at simulator, it can clock about like 40 trillion steps per second. But still, if you look at 40 trillion, can be like, I don't know, like it's 2 to the power something. But already you can see that if it's like 40 trillion, I don't know, 2 to the power x, but already you can see that this x will be way, way smaller than that. So for example, if you had like, you wanted to compute Fibonacci of 20 on the super fast computer, like it can take at least like, 2 to the power 92 seconds. Okay. So like if one of the fastest machines today, the time it takes is like, it's basically like the time for you to live, the time it will take for, people who love physics to say, like the time it will take for the sun to become a red giant and all. So yeah, you can't like have like, even though this definition of Fibonacci mathematically is correct, but now when you want to like write your code, we can't rely or use it because it's it's not much practical. So that's why, like, from having like an exponential algorithm, we then ask ourselves, can we do better? And yeah, we can do better. Like on our last lecture, we just saw an example of like how we can, basically like use memorization to remember the previously computed value so that we won't actually have to do all those steps again. And that algorithm, you can like look at it in the notes. It just takes like way less time, and you can even like compute like in seconds on your machine. You can compute fib of 200,000, but right now don't try to compute fib of 200 or like even 100 on your laptop if you still like your laptop. So yeah, yeah, that's it. That's it with just this introduction of fib. Any questions? Any questions? Any questions? Okay. Yeah. So to understand our question, like we have the big O notation, which I also like had on the slide. So basically, like you know, if we're thinking of this in terms of like recurrence relations, T of n, no, we're just being too precise, but sometimes we just like care, about like, some simplifications, and that's what your interviews, they most like, care about. So just like some rules, like, just summarizing to you, like, what, yeah, what big the big O, like, talks about, so when faced with a complicated function, let's say you have a function which is equal to 3n squared plus 4n plus 5, so what we just do is we find the simplest case for this one. So if we look at this, we're like, okay, what's the limit, like so like not like, okay, not what's the limit, do not define the limit, but as n approaches infinity, like which one grows faster? So like if we look at this, we're like, okay, this one will grow, this n squared term will grow faster than these other ones. For example, like, yeah, this will just be changed compared to the n squared term. And so like, we can just drop this one. And then this one, we multiply it by 3, but if n is now like, in the quadrillion or like something, as n approaches infinity, either multiplying it by 3 or multiplying it by 100 really won't make that much of a difference in terms of comparing how focusing on the bigger picture. So for example, if you had a function which took this number of computer steps, then it executes what in big of n squared. Okay, so now there are some rules, like which just, if you are analyzing your algorithm, let's say you have your for loop, and you have the for loop which runs, like you have the first for loop, and then another for loop, maybe you have like 100 of them. So, a for loop runs in linear time. So if you have 100 of them, you can still say that your algorithm is what? It's in linear time. So yeah, we'll see that with an example, like right now. So questions. Okay. So now let's get to like solving one of the problems which we had. So I'm going to see, like the thoughts from people, uh, what we, okay. So which question should we attempt together? Which question should we attempt so that we can like solve it together? Yeah, I'll take, yeah, I'm looking at the chat and taking in thought. So, oh, okay. Oh, people that are saying question 1. Okay. Or question 2 or 3. Oh, Someone said question 2 again. Oh, okay. Oh, okay. Someone said question 3. Yeah, okay. You guys, you don't have any preference. Okay, did someone attempt, no, like, question 1, did someone have a challenge? Does someone want to like ask anything? So I figured that, like people were not asking me questions. Maybe they perfectly understood everything and I didn't want to bother them. Okay, okay. People understood. People understood. Let's look at this one, for example. Okay, question 2. Yeah, Robert said question 2. So how can we solve? How can we solve question 2? Okay, so I think people, they can like unmute their mics, so that like they can give us. So now it's like, this complicated idea of big O and all. We just want to like follow those 3 steps of first finding a correct algorithm, and then now, finding the time it takes for the algorithm to run, and then asking ourselves if we can do better. So those, I think, 3 rules, they just allow us to like to know how to be able to move on. Okay. So let me, unmute people so that you can hear what they have to say. Okay, so any thoughts, ladies and
gentlemen? Perhaps you could first start by sorting the array.
Okay, so let's okay, so you say like this array. Okay, let me take screenshots of this. Okay. Okay. So you said like, we can start by sorting the array. Okay. So the approach is, okay. Approach 1, we sort the array. Okay. And then when you sort the array, what will we do after that? So
Pardon?
like after sorting the array, then how do you find the smallest missing positive integer?
Oh, yeah. So I think maybe someone giving an answer. Okay, so maybe you iterate through the array and then check if the value at the current index is less or equal to the value at the next index.
Okay. Then
so
and then compare values at corresponding, like like the next, I don't know which way to use, but like the one value. Okay.
yeah, the two values following each other, compare them.
Okay. Compare.
Sorry, I need to go collect my food, man.
No,
I don't. I
collect.
think.
Collect. Okay. Following each other. Each other. Okay. So other people, like, so like with this approach, so if we've sorted the array already, like we know that the values, like they'll have to, so we have to like what, compare the values. How did people approach this problem? Yeah, I'm curious to hear how they solved it, like, you know, getting a solution which worked.
Right now, what I'm thinking is the first thing that I would do is check if the maximum value in like this array is a negative. So if it's negative, then I think the first positive would be 1.
If the maximum value is negative, so like if all the values in the array are negative.
Yeah.
Okay. Okay. So that's like, okay. So you basically run through the array just checking if each and every number is right, is negative.
I'll check the maximum. So if the maximum value is negative, that means all the other ones are also negative. So I'll return 1 for that case. And
Oh,
then, yes.
okay. So if so what you're saying is you know, you just check for maximum if it's negative, then you know that the like the positive one, like the smallest missing positive one.
Yes.
Okay.
And
Then
then
yeah.
and then since I have the maximum already, I think I would loop through all values in range maximum, and then check if maybe I in that range is in my array.
In range. So look through all the values. Yeah. So yeah, like yeah, if you look through like all the values, like, you know, provided by the range, you'll be comparing them to what, to the maximum.
For example, if my maximum is 3, I'll be looping through so for I in range 3,
Okay.
and then I'm checking if those values, for example, if for instance I'll start at 0, if 0 is in the array,
Yeah.
then up until I get to a point where maybe a certain value is not in the array, then I break.
Oh, okay. 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 So if that value is not in the array, then you break.
Yes, that would be my first smallest positive.
Oh, okay. 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 So yeah, so basically now it would be, so why did you have to then check for the maximum?
Why did I have to check for the maximum?
Yeah.
You mean in the for loop?
Yeah.
Because I'm thinking
So like yeah,
I'm basically checking for the first positive smallest positive number
yeah.
in my array, and I'm assuming Guti, I'm
So,
looping up until I get to maybe the maximum value.
okay. So when you get to the maximum value, and then
And maybe if I get to the maximum value and I realize Guti, there is no if I realize that all those values are in the maximum, are in that array, then I think I'm going to add the next one, like return the next one. For example, if I've got 1, 2, 3, then actually I'll return 3, the maximum. No.
okay.
Okay.
So if you have you know, if your nums it's equal to 1 and 2 and 3, what should you return?
So the first missing will be 4, I think.
Yes.
Yes.
Yeah, then the first missing of what will be 4. Okay. So now if you look through, so max, so you say you look through all the values in the range till the maximum. So you look till 3.
Yeah.
Yep. So like, how do you, what's the cost of finding the maximum? So in order to know that, let's say I give you like a long array, a list with like 1,000 values. So like, for example, what would be the cost for you to like find which one is the maximum? So do you mean like, is there like a way of comparing? For you to find the maximum, you should have compared it with all the other numbers, right?
Can I just use the function max?
Yeah, like what's the runtime for the function max?
I think it's n log n. No, actually it's n. O n.
It's O of n.
I think so. Because I'm looping through, like I'm going through the whole array to find the maximum.
Yeah. And as you go through the whole array, what do you do?
As I'm going through the whole array, what?
Okay, so the max, you go through the array and then you compare like values by just going through the array. So maybe you might just keep a track that, okay, the max one is it's, for example, here you can start with having maybe the max element is equal to 1. And as you look through the entire array, you'll be comparing. So are you saying you'll be comparing maybe 1 to 1, then 2 to 1? If 2 is greater, then you change the max up until when you finish. By finishing, like iterating over the entire array, then you would know which one the max is. Okay. That takes like linear time. Okay. Okay. So like okay, we've understood like, okay, this that's the runtime, and then now when you then look through the negative, also you say it. So what if like you have yeah, so not like I'm not putting you on the spot, like other people should just like, no, can come, feel free to just come in and like, yeah, and pitch in how you, yeah, like your other thoughts on like solving this.
I missed a part of this explanation that Wizard Pumzile is giving.
Oh,
So
okay.
maybe take me back a bit and then.
Oh, okay. So, okay, I think like to drive the discussion, let's put maybe some let's put some constraints, like just like how would want to how would want to like solve it. I think there's some yeah, I think it's fine now. Okay, so let's try to solve this using a time complexity of n and the space complexity of 1. So this one means like it's this is linear time and this is constant. Okay. Yep. So like so from here, like I think I can drive the discussion from here, and then like people have questions in the chat, you can like ask or unmute, and then like yeah, let's talk. Let me drive you to talk through so that we can finish this problem within like the given time. Okay, so if we look at let's say for example like so solving algorithms, they're usually just different ways. So I might have one way of solving it, someone else might have one way of solving it. So that's like after those algorithms, you can like just run a check to see, what's the time complexity, what's the base complexity, and can you do better? And then like if you can do better, then you can like figure out, how to solve it. Yeah, in other ways which can be faster. Okay. So now let's say we have like and the number of elements. Let's say it's equal to 8, meaning like for example, if I have 1, 2, 3, 4, 5, 6, 7, and 8, if this is nums, okay, then the first missing positive integer will be what? In this case, it would be what? It would be 9. Okay. Let's look at another different case. If I have maybe like 1, I just want one where I'll just like 2, maybe another big value like 48, maybe like 24, 15, 16, 17, 18. Okay, let me just have one last one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, maybe let me have 12. Okay. So if we look at these ones, we can basically see that, okay, here we would want it to return what? To return 3. And here we would want it to return what? To return 8. Okay. And then what's the maximum possible? Like, what's the max possible? Like, what's the maximum possible, like first missing digit number? If the number of elements is 8, we know that the maximum they can ever be. But like going through this, like this one shows all the other elements in their order. So the maximum possible first missing number is what? It's n plus 1. Okay, it's equal to what? It's equal to 9. Okay, for example, we're just adding this 8 and 1 to get this 9. So looking at the number of elements, we can basically see that the number of elements determines and it governs how we can like think of this, how we can think of this problem, of the solution. Like we know that we can never have like the maximum possible which will be greater than 9. It can't be 10. Because if you say it's 10, then where is 9? Or if you say, oh, you have 9 in your list, which means then another number should be missing, which should be the first missing positive integer. So now, like if we're looking at this, we're like, okay, what if like, you now have a list with like negative numbers and all. So we can like we can try to get rid of to do some like data cleanup. For example, how important are negative numbers, for example, like in determining yeah, in determining like, our solution, or how important are like, like numbers which are greater than which are greater than which are larger, like which are larger than our length, for example, of the digits. Let's say, let me give you an example. Let's say if we had these numbers, 3, and we had 4, and we had -1, we had -2, we had 1, we had 5, then we had 16, 0, and 2, and 0. Okay, so if we look at this, for example, we can see that how many digits are there? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can see that what our n is equal to what? N is equal to 10. So by just like looking and scanning through that, we know that using like just this observation, the maximum portion of the first missing digit should be what? N plus 1, which should be equal to what? Yeah, it should be equal to what? To 11. Okay, so let's say, okay, if we know that we've we're done like searching for this one, let's try to say, okay, what's the case when your answer will be 11? That is, if 11, if all these numbers, they are from what? From 1 to 10, then you know that, okay, you have searched through your entire like list, then your answer should be what? Should be 11. Okay, so now let's try to then like to clean up our list by like, replacing you know a like negative numbers, and also like replacing 0, or and also like numbers greater than n, like numbers greater than n. So what we want to have is, we want all the values, we want all the values in nums to be within 1 and what? And n. Okay, so now we can just go through like the negative numbers and the 0 numbers, and the numbers which are like 0, or numbers which are greater than n. We can replace those, maybe with with some dummy like a variable. So let's say like, okay, we can replace them with the integer 1. But in order to first replace with the integer 1, we first have to ensure that, okay, the first missing positive number is not 1. So like, for example, you can like just go through, before you do like the data cleanup, you can just go through to search, if 1 is in that list. If 1 is not, then you can now do your data cleanup and see. So by the data cleanup, what we'll be doing is we'll be taking that. Okay, let me shorten it a little bit. So when we clean up our data, what we'll get is we have 3, and then we have 4. Then we'll replace -1 because it's a negative number. We'll just replace it with 1. Then we'll replace 2 with 1, and then we just keep 1 like that. Okay, and then we'll replace, we don't replace 5. 16 is greater than 10, so we'll just replace it with 1. Then we'll also replace 0 with 1. And then we have what? We have 2, and then we just have that one, like 1. So let me just highlight here to see which numbers did we replace. So we replaced this one. Okay, then we also replaced what? Then we also replaced this one. Okay, then we also replaced, this, yeah. So now we've ensured that our array now has numbers which are just like within that range. You know, they are all like either between like 1 and n. So n being 10. Okay. So now we want to solve it now, you know, like in linear time and using constant space. So constant space meaning like, you know, we don't have to like create another array. Let's just use nums to see, you know, how we can like optimize on that. So now if we look at these numbers, okay, and then you start thinking like, you know, how can you like attempt, for example, to solve it with a solution. So right now we've replaced the negative numbers and the numbers which are 0 or numbers which are greater than n. So now we can if we had if we're not limited to using constant space, okay, let's see, like for example, if we had okay, let's say if not limited by constant space, okay, then we might have for example a space complexity solution by using what? A hash map. A hash map, that's like, you can just think of it as, you know, some dictionary. Okay. So by using a hash map, what you'll basically be doing is a hash map keeps track. Okay, let me use a different color. A hash map will keep track. For example, if to say you then have these digits as their values, and then you like also like have some count. For example, you know, like you would it to just map a positive number to its presence. Okay. So for example, you like, okay, as you go through that list, you're like, okay, you have 3, and then you have 1. You know, so going through the list, it will be adding, you know, like dictionary, like adding to the key, which would be like, you know, the number. So like you would have counted like 1 or how many, 6 times, and then you'd have counted 2 once, then you'd have counted 3 once, and then 4 like once, and then 5 once. So as you are going through, you know, when you reach 6, you know, it will just know that, okay, 6 is missing, you know, because you didn't have it, like, you know, it's not there in your, in your hash map. But then how to be, let's say if you didn't want, there's actually like a neat trick here. For example, if you, we see that we want to have this idea of like, of a hashing, like a matching, you know, like something to some persons. So we can now like reuse, for example, you can get the constant space complexity solution by using a string. Okay. So basically you use, you know, a string as a hash map. So if you, for example, like with with you initialize, for example, like if you know that, okay, your n was equal to 10, what you can just do is to initialize 0, 1, 3, 4, 5, 6, 7, 8, 9, 10. You just initialize, you know, a hash string. let's say you initialized a hash string which has these 10 values initially as 0. And now you can use it. You can then use this string to behave like your hash map. But you know that the difference is this string will always, because you have initialized it with what? At the first time, like, with you have allocated it like some block of memory. So that block of memory will always be fixed. So now what you do is every time, for example, you can, like when you want to, you can use it to, for example, to keep track, of the, to keep track of the numbers. For example, if you say that, okay, how many times, like, do you have, like if you meet one, you can just like switch this one, like flip it only once, like so that you can like be careful of this duplicate. So looking at these numbers, for example, these numbers, what would get as our solution here can be, we know that 1 is there, 2 is there, 3 is there, 4 is there, 5 is there, 6, 7, 8, 9, 10. So now this string, then you know that, okay, yeah, this is this is what n is equal to 5, and then this is what n is equal to 6. So then you know that now this string will keep track of your state, which indicates the presence of a number. So now when you then look through that string, then you can basically like figure out that, okay, wait, n it's n is it's 0 here. So like, which means this should be what? The first like missing number. Let me see if people have questions. Okay. I have no questions. No. I like how you guys, you're actually understanding this so smoothly, like 10 out of 10, 10 out of 10. Good, excellent, 10 out of 10. So yeah, so like, yeah, that's one solution of just like, thinking on how to solve this using this idea of a hash, as a string. So any other, did someone solve it a different way? For example, like I know like there's also a way of solving it using, like by using like, the index of the array as a hash key, and then like using the sign of the element, for example, like, as a hash value to like, if the, like going through the, you're now going through this cleaned array, for example, and then like what you'll be basically doing is you'll be checking if, going through the cleaned array, you'll then be checking if, oh, for example, when you have like 3 like this, what you do is you look through your array, and then okay, let me use this example. You look through your array. Let me copy this. Paste it here. Okay. So yeah, another example would be like, okay, when you've cleaned up your array, you can like look through it. For example, when you get 3, and then you can change, okay, the element at position 3. So you use this, for example, to indicate your positions. So the element at position 3, you change it to be negative. If it's not already negative. So by 3, this will be what? Will be negative. Okay. Because like you can think of this as position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're using the index of the array, and then you are mapping it to, like, the sign negative or positive to indicate the presence of a value. So like you're like, okay, at 3, that's -1. And then now when you look, you are now looking at 4. Then you go to the element which is at position 4. Then you also like that changes thing there. Okay. And then now when you then like go to this one, so you'll be now looking at it like, in absolute, using the absolute value. When you look at this one, then you go to the element at what? At position 1 and change its value. When you look at this one, go to the element at position 1, take the absolute and then change its value. It will remain like -3. That's the same also with this one. Then now when you look at 5, 5 for example, what you are doing in this case is you are going through the first, the element which is at position 5, that's this one, and you are putting a negative to it. Then this one and this one, they're still changing the first digit. Then now when you look at the element 2, so you now go to this at position 2, and then you check the digit, and then you look for the last one. You also see that it also just modifies that. So now after you have finished going through your array, so take a look at this. The first five numbers, they are signed. First 5 numbers are negative. So with them being negative, basically you know that the next one, for example, there's no sign of a negative. So if 6 was there, then you would have, know that the reason why a number changes its sign is you find that number. For example, why did 4 changed? Why did this one change its sign? Because there was this number. So you just identify the number, and then you change the sign of what? The number at that index. So now that will make sure that already it's ordered. So you can just solve your your code in time complexity is constant time, because it's just running through loops once. You might have maybe 2 or so loops, but that just becomes a constant. For example, maybe let's say in this case, you might run it the first time to check if 1 is nums, then you run it again, to replace the zeros, and then you run it again to using this, using this logic. So let's say if you run maybe 5, for example, 5 for loops, then those 4 loops, if each loop runs at linear time, then you just know that what you have big O of 5n, or plus some other constant. But then we know that we throw away the constant, then we also throw away this other one, because there's no difference in the big picture between 5 and n. The growth of these two, they're just the same. So sometimes, if they say, oh, we need a solution to be in linear time, most people, they'll just think of, oh, you should only have 1 for loop and all. But no, you can have like, you can look through multiple times, because you know that those multiple, you can look through the same thing multiple times as long as they are not like nested for loops. Nested for loops can now give you like quadratic time, but you can look through maybe at least multiple times. When you like just look at all those times together, they're just like it's just multiplying by a constant, and as n approaches infinity, that constant really doesn't matter. Okay. Yeah. So let's see. So did you go through a simpler way of solving it without looking at the constraint? So like, so for to speed up, for example, like since I knew that there was a better way of solving it using like constant space and linear time, I just started with that so that it's kind of like in the interest of time or streamline our solutions into just like focusing on like how to get like an algorithm which might be like more efficient. But mostly it usually starts with the brute force approach. For example, the brute force approach in this case, my brute force approach was using a hash map, which was going to have of n space complexity. But then I was like, okay, I can actually also improve on that complexity by first trying to think of using a hash string, which I knew was going to give me constant space complexity. And also, like just now discussing this method, it also gave us constant space complexity. I hope I answered some question.
Yeah, thanks, man.
Oh, okay. Yeah, we're left with 4 minutes or 6 minutes. It's like question. Yeah, so yeah, I'm free to like, yeah, to reach out to me and then like.
I joined late. Like I didn't know the lesson was starting at 12.
Oh, okay.
So like any advice on how I can catch up on this stuff?
How you can catch up on this?
Yeah.
Oh, okay. You can like you can like always come to ask me questions. Like if someone like you need help understanding maybe like more on this homework program, since like yeah, I'll make sure like the people in the class, so like since this is more of a hands-on thing, then there are like less of you, so I can give you like I have the time to like help people understand. Okay, what's the mechanism of submitting? So yeah, I will add yeah, so you'll get a link right after this to sub yeah, mostly. Yep. So there's a platform called Grayscope. So what you do is yeah, when you okay, let me okay, yeah, if I show me the net release like uh, student information. But so there's a platform called Grayscope. So when you log into Grayscope, and they need to ask you to drag your files. So you submit the Python file, so like q1.py, q2.py, q3.py, q4.py, and q5.py. Even if you didn't complete them, just submit them. And then when you submit them, then I'll do manual grading. I'll automate some of the stuff just to see, like, for example, is the algorithm correct? Basically, I'll just be testing the code in the doc test. But then I'll do manual grading by looking at people's code individually and then giving people feedback, yeah, on that. So even if you like, you attempted a solution and then you don't think like it's the most optimal solution, just submit. The point is like, by submitting more, you get feedback, and then it also helps for me to understand like, the thought process, how you actually like came up with those lines of code, where you started, where you ended. And then from there it becomes easier to assist you to like really like develop the skill of problem solving. And then one other thing, I think maybe I do it more like, and I'll also like notify people like on the WhatsApp group, or also send an email to sign up for like the first slot. So the first like interviewing slot that you guys will like, your first interview with me is just like giving someone one question, a 45-minute slot. So I'll just release them, and then people like over the next week, people that can just sign up, and then we'll just go through like we'll simulate a technical interview. Okay, do we get some credentials to get into Grayscope? So yeah, so you just have like an email, which then you create an account on Grayscope. So when you create that account with that email already, I would have added you to the course, or else you have like some course entry code, which I would also like release if I failed to add people. But I think I have like everyone's email address, so I can just like add it. Or if you prefer to like sign up with a different email, just let me, especially like for people who registered with their institutional email, so that in your school uses Grayscope, we don't want to like mess up that order in there. So maybe like if you want to use maybe a Gmail account, you can like just let me know, and then I'll sign that up, yeah, as well. Or actually, I think the easiest way, I'll just create a code right now and then post it on WhatsApp, then people can be able to sign up on themselves. So you create an account on Grayscope, and then when it says add course, you'll then add that course ID, But like if no one is not connected by the end of the day, like feel free to like let me know at any time. Yeah. And then yeah, I want to encourage people, reach out to me. Oh yeah. So yeah, I'll send the course entry code, and then so that it will be easier for you to like sign up, and then it directly links to the course. Yeah, definitely. So please reach out. These problems, they are very hard to solve, and I don't expect that like you should like solve all 5 of them or get all of them correct. It's just like from going through them, we just want to practice the approach of like how do you approach problem solving. So if you are comfortable during an interview, basically like the interviewer will be like, giving you some guidance and asking you some questions. So we just want to like prepare people for that. Okay. So it's 11. I think the time is up. I'll just